This is Physics 2211, Lab 4, Oscillations. In this lab report, I will first introduce the experiment and then explain its two components, the tracker analysis of the object attached to the spring and the computational model to predict its motion. I will then follow with the results, discussion, and the conclusion. The first purpose of this lab is to compare the observed motion of an object attached to a spring with the predicted motion calculated using a computational model built in GoScript. The second purpose is to plot the system's energy changes that are computed in the model, delta K, delta U grav, delta U spring, and delta E total. The fundamental principles in this lab are Newton's second law and the energy principle. Firstly, Newton's second law states that F net is equal to the change in momentum over the change in time. From this equation, the following velocity and position update formulas were derived. They will be used in part 2 of this experiment to predict the motion of the object attached to the spring. Secondly, the energy principle states that the change in energy of a system is equal to the work done on the system by the surroundings plus the transfer of thermal energy between the system and the surroundings. In the experiment system, there are no surroundings because the system is the spring, the object, and the earth. They interact with each other to give rise to potential energies like the kinetic, gravitational, and spring potential energy. W sir is 0, so the sum of the potential energies is equal to 0. The result of this experiment is that the predicted motion is similar to the observed motion. However, the model overpredicts motion in the y direction with a closer estimation for motion in the x direction. Also, the change in total energy was found to be 0, which we'll see in the coming slides. The tracker analysis of the sample video is shown here. The initial conditions are a mass of 0.402 kilograms, an initial position of negative 0.111, negative 0.631, 0 meters, an initial velocity of 0, 0, 0, a start time of 0 seconds, and an end time of 9.402 seconds, and the video was shot at 10.53 frames per second. The spring constant Ks is equal to 6.83 newtons per meter, and the relaxed length L0 is equal to 0.123 meters. They were calculated from the video and tracker data, and the equations used are shown on the slide. The system is the object, spring, and the earth. There are no surroundings. I set my axes as positive x to the right and positive y upwards. A key assumption is that there is negligible drag force acting on the object in the video. Here is the code used for the computational model to predict the object's motion. The initial conditions and equations from the introduction are shown in the excerpts of code. The while loop calculates the net force, which is the sum of gravity and the spring force. The net force is then used in the velocity and position update formulas to predict the motion of the object. The potential energies are calculated iteratively, and the change is found through final minus initial. The total energy is defined as the sum of the kinetic, gravitational, and spring potential energies. Here is the result of the code. Delta U grav and delta U spring are opposite in sign and are oscillating function. Delta K also oscillates but is smaller in magnitude and not aligned with delta U grav and delta U spring. The orange plot representing delta E is a straight line as 0, suggesting no change in energy throughout the object's motion. For the x position, the model's graph seems to be offset in the x and y direction. It is more accurate in the beginning and deviates as time increases. For the y position, the model is quite accurate except for an overprediction of the object's motion as seen by the greater amplitude of the graph. These deviations are likely due to these potential sources of error: neglecting the drag force on the object, inconsistency in marking the center of the object in tracker, rounding errors compounding within the computational loop, and the fact that the values for K and L0 were taken from pre-lecture video 52. These values may have differed if calculated from the video used in this experiment, and this may have caused the differences between the observed and predicted motion. For the further questions, yes, the energy principle is satisfied in my model system. The results show that delta E, defined as the sum of delta K, delta U grav, and delta U spring, is equal to 0 as seen by the orange line on the graph of potential energies. For the oscillation period represented by the variable t, which is the time period between two crests or troughs in the position versus time graphs, the period of oscillation for the x position is 1.638 seconds, and for the y position is 1.500 seconds. The difference is 0.1378 seconds, which is significant. The period of oscillation is used in the calculation of the spring constant and the relaxed length, which affects the spring force and spring potential energy calculation. This difference could be caused due to the potential sources of error outlined previously, for example, the ignored drag force or human error in tracker. For the conclusion, the model predicted the observed motion to a certain degree of accuracy, but it displayed deviation in both x and y directions. The energy principle was satisfied in the model system as delta E was found to equal 0. Thank you.